This is our PC controlled DC power supply with built-in fire warning lights for ECE 342 winter 2024. Your team EGA 17.
I'm Matan Shapira.
I'm William Davis.
And I'm Noah Bean.
So let's look at an overview of the system. So basic information, 7 weeks of work time, 2 to 14 voltage range, 2 to 14 voltage range, DC power, accuracy of 0.1 in voltage range, up to 1.5 amps of current in the voltage range, PC control.
So there were separate blocks with this system. One of those blocks was the graphical user interface. Another was the button user interface. There was also a microcontroller. There was a visual display, heat sensor, and a DC to DC converter system. And this is a block diagram for the project, which describes who did what. So the first block was the power converter system. This block is a power supply that has 2 inputs and 2 outputs. The 2 inputs are a DC power supply and a signal from user. The 2 outputs are 2 power channels. So on the left is a block diagram in LT Spice for a buck converter. And on the right is a buck converter module, which is a device used to step down power from 20 volts to the 2 to 14 volt range that was required for this project. In order to step down this voltage, we used digital potentiometers. These potentiometers change the voltage and the current, and there were 4 included in the system, 2 for each channel. They are controlled by the Arduino code. The next block was the button interface. This button interface has 3 inputs and 1 output. The 3 inputs are a DC power supply, a microcontroller, and the button array. The output is a digital array that indicates user input. And this is a block diagram of the button interface written in KiCad.
This system is a fire alerting LED. It was designed by me and it was used to alert us if there is a fire within the power supply. It is not physically connected to the rest of the power supply components and it is on a PCB. It uses a potentiometer to set the sensitivity of the sensor, and it uses a BJT to actually detect and increase in temperature. To the right, you can see the simple circuit design, which I made, and to the left, you can see the PCB that we've ordered. We can also see the PCB design, which was based on my circuit design and was designed by Noah. And you've already seen how it turned out in the end. These are the INA 219 current sensors. We have used those to function as a watt meter. The sensors have a built-in ADC module and they're operational up to 26 volts. They can easily handle the necessary 1.5 amperage, and they are easily integratable with our microcontroller and with our display module. Here is our display module, which I've designed and coded for. Here you can see the simple block diagram for it, as well as the implementation of the casing to house the LCD.
Next is the graphical user interface. This is based on on a computer and it connects to the Arduino Uno R3. It controls both voltage and current channels for channel 1 and channel 2, controls both voltage and current, has a range of 2 to 14 volts and 0 to 1.5 amps. Next is a microcontroller. The microcontroller takes in all the information from all the other blocks and it sends that data. It outputs to the display. It outputs a pulse wave to the DC to DC converter, and it outputs a signal to the digital potentiometers. Lastly is the casing. It is used to store and hold everything in the project and thus has to be big enough to hold every single component with room so that it is not all on top of each other, making a bigger fire risk. It also is designed so that it can withstand the shake test and a drop test. And there is a lid, as shown in the bottom picture, to prevent water from leaking in. And it is big enough so it doesn't catch on fire. So what worked? What worked well, the DC to DC converter could convert down from the input voltage of 20 volts down to the range of 2 to 14 volts, while still having the current be up to 1.5 amps. The heat sensor worked as intended. The graphical user interface is able to interact with the system. The display also works very well, and so does the casing.
What didn't work? The voltage and current control did not work as we intended. We could influence the voltage and the current, but we could not directly control it at this point in testing. The digital potentiometers could also similarly be controlled, as in they could be influenced to increase an average or decrease an average, but they could not directly be controlled as intended. Time was not managed as well as should be. There are days and weeks where we should have met and we have not, and there are days where we should have probably not have met so that we could manage workloads for other classes. And then communication between team members could have definitely been done better because we would have had better information about each other's blocks and better integrated the system.
If we had more time, we would have added many more components. We could have added a rectifier to the system. A rectifier is a device which is able to convert AC power from a wall socket into DC power. We could add an inverter, which would convert DC power back into AC power. We could have had a third channel that outputted AC power. We could have used more advanced converter topologies instead of a simple buck converter. We could have used for example, a flyback converter, which would have the capacity to increase and decrease output voltage and also be isolated by using a coupled inductor system. We could have increased the accuracy of the system by using a potentiometer with more wiper blades on it. We could have increased the efficiency of the system by adding some more components to it. However, the efficiency of the system was generally fine. We could have used a more powerful microcontroller. We used an Arduino Uno, which is a relatively cheap power source, but we could have used a microcontroller with more pins. We could have included a snubber, which would have reduced switching loss, thus increasing efficiency in the system. We could have displayed power with the LED display, the LCD display. The LCD display currently has voltage and currently has current, and so it would be relatively simple to just multiply them together to get power. We could have gotten the system to operate with a single microcontroller. Currently, the system operates on 2 separate Arduino microcontrollers. And we could have used a multiplexer for more efficient button handling, because the reason we had to use 2 different microcontrollers is for one to act with the button interface system.
Welcome to our TED Talk. Thank you for stopping at our TED Talk.